Welcome to the course on solar energy in second semester of MTech, Renewable Energy Technology. I am Bharat Kumar Saxena, guest faculty at Department of Renewable Energy, Rajasthan Technical University, Kota. Let me just outline what I will be discussing today in lecture 1. First, we will take a brief look at syllabus and lecture plan that I will be following. I have divided whole syllabus in a series of 42 lectures. The title of today's lecture 1 is Introduction, Solar Energy Basics and Sun Motion. The syllabus of solar energy is as follows: solar radiation, its measurement and prediction, flat plate collectors, liquid and air type, theory of flat plate collectors, advanced collectors, optical design of concentrators, selective coatings, solar water heating, solar dryer, solar still, solar cooling and refrigeration, thermal storage, conversion of heat into mechanical energy, and active and passive heating of buildings and solar cells. So I divided whole syllabus in the form of subtopics and 42 lectures. They are as follows. Solar energy basics and sun motion. The sun is a sphere of intensely hot gaseous matter. Sun is in fact a continuous fusion reactor with its constituent gases as the containing vessel. Several fusion reactions have been suggested to supply the energy radiated by the sun. The one considered the most important is a process in which hydrogen combines to form helium. The mass of helium nucleus is less than that of 4 protons. Thus, the mass having been lost in the reaction and converted to energy. The structure of the sun is as shown in figure. It is estimated that 90% of the energy is generated in the region of 0 to 0.23 R, where R is the radius of the sun, which contains 40% of the mass of the sun. As shown in the figure, photosphere, outside of the photosphere is a more or less transparent solar atmosphere observable during total solar eclipse or by instruments that occulт the solar disk. This simplified picture of sun, its physical structure, and its temperature and density gradients will serve as a basis for appreciating that the sun does not, in fact, function as a black body radiator at a fixed temperature. Rather, the emitted solar radiation is the composite results of the several layers that emit and absorb radiation of various wavelengths. Solar constant, Earth Sun relationship. Figure shows schematically the geometry of the Sun Earth relationship at a distance of 1 astronomical units, that is 1.495 into 10 to the power 11 meter, the mean Earth Sun distance. The Sun subtends an angle of 32 minutes. The radiation emitted by the Sun and its spatial relation to the Earth results in a nearly fixed intensity of solar radiation outside the Earth atmosphere. The solar constant is the energy from the sun per unit time received on a unit area of the surface perpendicular to the direction of propagation of the radiation at mean earth sun distance outside the atmosphere. Spectral distribution of extraterrestrial radiation. In addition to the total energy in the solar spectrum, it is useful to know the spectral distribution of the extraterrestrial radiation, that is, the radiation that would be received in the absence of the atmosphere. A standard spectral irradiation curve has been compiled based on high altitude and space measurement. The World Radiation Center standard figure is as shown in figure below. Table 1 provides the same information in the numerical form that was provided in the previous figure of World Radiation Center spectrum. Here, G is the energy in watt per meter square micrometer over small bandwidths centered at wavelengths lambda and is shown in the second column. The fraction f 0 to lambda of the total energy in the spectrum, that is between wavelength 0 and lambda, is given in the third column. The table is in two parts. This is first table at regular interval of wavelength and this is second table at even fractions of f 0 to lambda. Now, based on the work that we have performed, a numerical question can be attempted. Calculate the fraction of extraterrestrial solar radiation and amount of that radiation in the ultraviolet, visible, and the infrared portion of the spectrum. One hint that I can give you is that use the tables that are provided in the previous slides. Variation of extraterrestrial solar radiation with time of the year. Now, the solar radiation received at the Earth's surface varies due to 2 points. Variation in the radiation emitted by the sun, but it is less than plus minus 1.5%. And second variation is due to the variation in the Earth-Sun distance. The variation of Earth-Sun distance, however, does lead to variation of extraterrestrial radiation flux in the range of plus minus 3%. The dependence of extraterrestrial radiation on the time of the year is shown in figure below. A simplified equation with accuracy adequate for most engineering calculations is given in equation where G on is extraterrestrial radiation measured on the plane normal to the radiation on the nth day of the year. Solar time, also known as local apparent time. Solar time is measured with respect to solar noon, that is the time when sun is crossing the observer's meridian. At solar noon, sun is at the highest position in the sky. The standard time is converted to solar time by incorporating two corrections. The equation for calculating solar time is shown here, where LST and LOC are the standard longitude used for measuring standard time of the country and the longitude of the observer's location respectively. The plus sign is used if the standard meridian of the country lies in the western hemisphere with reference to prime meridian and negative if that lies in the eastern hemisphere. The E in this equation is the correction arising out of the variation in the length of the solar day due to variation in Earth's rotation and orbital revolution and is called equation of time. The solar day, which is the duration between two consecutive solar noon, is not exactly of 24 hours throughout the year. The equation of time correction in minutes can also be calculated from the equation given below. Now, based on the knowledge that we have gathered, second numerical can be performed, that is, determine the local apparent time corresponding to 14:30 hours Indian Standard Time at Mumbai. The coordinates of Mumbai are given and the date on which you have to find is on 1st July. I have also provided its solution. It can be solved like this. Now, Earth orbit is not circular. Also, Earth is tilted at 23.45 degrees. Due to this, various seasons arise on our Earth. On 21st June, summer solstice occurs and 21st December, winter solstice occur. Between these two positions, 21st September and 21st March are known as equinox. Direction of sun rays during summer and winter solstice decides whether it is a winter or summer in the northern or southern hemisphere of the earth. As shown in the figure right side, on 21st June, the Tropic of Cancer is near to the sun. That means northern hemisphere is tilted towards sun and southern hemisphere is away from the sun. So in the month of June and onwards, there is summer in the northern hemisphere and winters in the southern hemisphere. Similarly, during December month, the northern hemisphere of the world got winter, whereas southern hemisphere the season is summer. Now, this is the very important and interesting part if you have to perform numericals of solar radiation. So, you have to understand what do you mean by solar radiation geometry. The incident radiation depends on solar geometry involving several basic and derived angles. The three basic angles are latitude, hour angle, and declination angle. Latitude indicates location on the earth, hour angle indicates time of the day, and declination indicates day of the year. The hour angle is based on local solar time. The declination varies in an approximately sinusoidal fashion. Now we can geometrically define what is latitude angle, what is hour angle, and what is declination angle. Latitude is the angle between the lines OP and the projection of OP on the equatorial plane. Angle AOP, shown by L here, but standard convention of latitude is phi. Our angle, shown by H here, is the angle between the projection of OP on the equatorial plane, that is line OA, and the projection of the line joining the center of the earth to the center of the sun, line OB, that is angle AOB. AOB. This figure is also a replication of showing our angle, and this figure is for understanding declination angle. The declination angle is shown here, and this is equatorial plane, and this is the line of the sun. You can see that declination angle varies in a sinusoidal fashion for 365 days. Numerically, declination angle is can be represented by 23.45 sine 360 by 365 to 84 plus n. There n is the day number starting from 1st January as 1. The solar geometry, other than the basic angles, there are other derived angles, that is zenith angle, the angle between the vertical and the line of the sun, solar altitude angle, the angle between the horizontal and the line of the sun, solar azimuth angle, the angle of projection of beam radiation on the horizontal plane from south. If the surface is tilted, we represent the tilt angle by angle beta. There is standard. It is a standard convention to represent latitude as phi, declination angle as delta, slope as beta, surface azimuth angle is gamma, hour angle as omega, angle of incidence theta, zenith angle theta z, solar altitude angle alpha s, and solar azimuth angle gamma s. There is a set of useful relationship among these angles. Equations relating to angle of incidence of beam radiation on a surface theta to other angles are as shown in the equations. For a horizontal surface, the angle of incidence is the zenith angle of the sun, theta z. For this situation, beta is equal to 0, and the equation simplifies to this equation. For vertical surfaces, beta is equal to 90 degree, and the equation becomes like this. For the inclined surface facing due south, gamma is equal to 0, and by substituting gamma gamma in previous equation, we obtain this equation. Now, just for solving numericals, it is important to remember the following sign conventions. Latitude is measured as positive for the northern hemisphere. It can vary from minus 90 to plus 90 degree. Surface azimuth angle is positive if the normal is east of south and negative if west of south. It can vary from minus 180 to plus 20 degree. Hour angle is measured from noon based on local apparent time, being positive in the morning and negative in the afternoon. It can vary from minus 180 to plus 180 degree. Solar azimuth angle is taken positive if the projection of the line of sight is east of south and negative if west of south. Now, based on the sign conventions and the knowledge that we have acquired, a third numerical is given. The numerical is like this: calculate the angle made by beam radiation with the normal to a flat plate collector on May 1st at 9 hours local apparent time. The collector is located in New Delhi. The coordinates are as shown. It is tilted at an angle of 36 degree with horizontal, that is beta is 36 degree, and is pointing due south, that is gamma is equal to 0. So it can be solved like this, and theta comes to be 48.9 degrees. Now, based on the angles that we have studied, sunrise, sunset, and day length can be calculated. For the horizontal surface, the hour angle corresponding to sunrise or sunset on a horizontal surface can be found from this equation. If we substitute the value of 90 degree for zenith angle, we obtain this. It yields positive and negative value of omega s. S represents sunrise or sunset. The positive value corresponding to sunrise and negative to sunset. It also follows that number of daylight hours is given by 2 by 15 cos inverse minus tan phi tan delta. On the inclined surface facing due south, the hour angle at sunrise or sunset as observed by an observer on an inclined surface facing south will be given by this equation. If the day under consideration lies between September 22 and March 21 and the location is northern hemisphere. However, if the day under consideration lies between March 21st and September 22, the hour angle at sunrise or sunset would be smaller in magnitude than the value given by above equation and can be obtained from this equation. Thus, the magnitude of hour angle for an inclined surface facing south is given by minimum of the two. The next that we are going to study are solar charts. Solar chart is a pictorial representation showing the position of the sky, position of the sun in the sky at various times. Such charts are very useful in determining shading phenomena associated with the solar collectors, windows, and shading devices. The point at the intersection of the corresponding date and hour line represents the instantaneous location of the sun. This is a solar chart in Cartesian coordinate. Here, if we know the date and time of the day, we can calculate the solar elevation and solar azimuth angle very easily. Suppose if we choose the month, the solar path of Jan 21st, and at time 2 p.m., if we want to know what is the altitude of the sun, the crossing point is this. So we go left side, this gives the solar elevation in degrees, and on the right side, we get the solar azimuth angle. Sun rises in the east and it follows this path. At solar noon, it is at the highest highest position in the sky, and it sets in the west. Similarly, in the polar chart, solar chart can be represented like this, and we can find the elevation of the sun just by knowing the date and time. The references that were used in preparing this material are from Solar Engineering or Thermal Processes by John A. Duffy, William A. Beckman. This is the end of lecture 1. Thank you.